right? So which are going to be measured. I guess I will measure you as some of your capability, not all of your capability. So, but generally people don't like to be measured. So, but there is enough data to suggest that there is significant dependence. So it depends on the disciplined approach people use. It depends on the maturity of the programmer. It depends on how familiar the programmer is with the problem domain. But we took some data that was collected by two Japanese researchers, Takahashi and Kamayachi. And basically, they found, based on some limited data they collected a fair amount of data, but no amount of data is enough. They found that defect density declines by about 14% a year, up to 7 years. Okay, what happens after 7 years? So if you extrapolate it linearly, you will say that their model suggests that people should have a negative defect density, which of course doesn't make sense. So any kind of a linear extrapolation is valid only for certain range. So you cannot really extrapolate it too far. So based on their numbers, we took the assumption that defect density declines by about 14% per year, programmer experience, up to 7 years. And after 7 years, people are stuck with whatever they have, capability they have acquired by that time. So they don't get a whole lot better. It's a simple model, but if you come across a better model, let me know. Team's average skill, we phrased it this way, and here the multiplier. High, average, low, 0.41, which is default, 2.5. So based on their data, we felt comfortable in saying that if you have high capability programmers, then their defect density could be as low as 40%. And if you have really bad programmers, the defect density could be as high as 2.5. But again, I wouldn't guarantee these numbers because people really vary quite a bit. Because this is, there are some studies, but there are no good studies that will allow us to construct a very good model. But again, if you come across some, then let me know, so I will update this. So what do you think about this? Do you think this looks reasonable? So I guess you guys have gotten better in programming. So so you're probably around, so you're graduate students, so you're probably average.
Defect density is average per dozen lines.
Defect density is defined as the number of defects per 1,000 lines of code.
Okay.
That is true. So, but in this case, of course, it doesn't matter how you define defect density.
I see.
That's right.
But that is the definition we are assuming. Defects per 1,000 lines of code. So notice this is the multiplier.
I see.
So this is the relative number, right? So it's not the absolute number. So 1 is the factor. Yeah, that's a good point. I should point out. These are not the absolute numbers, but these are relative factors, right? And then there is a capability maturity model. Now there is a famous there's a famous organization, Software Engineering Institute, and they have a capability maturity model, which goes.
So the equation that was written earlier, which went like C times FPH, FPT.
Right.
So what is C there? Is that
C is some constant. So basically, assumption is that at first you estimate the value of C based on some similar projects. And once you have estimated the value of C, then you can use it to calculate defect density for newer projects. But you have to somehow, so that is referred to as calibrated. So you have a model, and you need to calibrate the model, you need to estimate the parameters. And once you have estimated the parameters, you can use, assuming the parameter value still holds, you can use it for a prediction. So we will see an example after we are done with looking at some of these factors. Now there is a famous capability maturity model that was proposed by the Software Engineering Institute, which is at Carnegie Mellon University. So this is Software Engineering Institute Capability Maturity Model. And so it is called SEI-CMM. That is well known in software engineering. But I think even, I don't know if engineers, have you heard about this? But it's well known in software. So basically they came up, so it was an effort, joint effort in 1986, Software Engineering Institute and MITRE Corporation. And so they had some government support also. And they did a lot of studies based on what was available, and they came up with some conclusions, and saying that a software development organization has a capability maturity. So there are some organizations that are more mature, and there are some organizations that are less mature. And this is what they said. So here is your SEI level. So at the lowest level, level 1, which is called initial, and the key feature of level 1 SEI maturity is the process is rather ad hoc, which means there is really no process. And then there is a repeatable process, and where there is some basic management of the process. And then there is a defined level, which is level 3, which is a higher level. And defined is there's some standardization. I guess I should have made this column a little bigger. And then there is a managed, where you have some quantitative control. So let me say quant for quantitative. In other words, they are using some numbers to characterize their process. For example, they are looking at their defect density and trying to improve defect density and things like that. And then 5 is optimizing. At optimizing level, they are doing everything, and they are doing continuous improvement. So this is the highest level of maturity. And based on some data that they collected at one time, they found that 75% of the organizations are at the lowest level, and there are about 15% here. So, and there are 8% at level 3, and there are 1.5% at this level, and very few, 0.5% of the organizations are at level 5. Now, it is possible for a group to be tested and certified. So there are very few organizations that have a level 5 maturity level. So you must have heard about this outsourcing business. So software development is one of the things that is often outsourced. So, and there are these software companies. So if there is a software company that is at level 5, and if you give them some work, they are going to charge you a lot more money compared with an organization here. Because of course, they are likely to be able to deliver much better software because they have a much better process. And now interesting part here is the defect density. So, so we looked at some numbers. And so we looked at some numbers by one of the researchers, Jones, some numbers by Keene, or some numbers compiled by people at Motorola. And actually we found the numbers vary, but kind of averaging them and rounding them, we came to this. So we took this as the default. Now the reason we took a level 2 to be a default, now as I said, 75% of the organizations are really here, but we argued that these organizations are not going to look at our papers anyway, so our work doesn't apply to them anyway. So most of the people who are going to be worrying about defect density would be sort of here. So I could take them as default. So, and this would be 1.5, 0.4, 0.1, and 0.05. So an organization with level 5, they can deliver software with much lower defect density, based on what we have seen. Any questions or comments? Okay, so now let us go to the next factor, the structure factor. Now, software structure, this is again another thing that has been investigated, including we have. And lot of controversy. And what are the things that are part of the structure? So one of them is assembly language code. So typically, okay, how many of you have been programming in assembly language? So programming in assembly language is not bad, but you are much more likely to make a mistake in assembly language code. So if you have a fraction of the program in assembly, and that is not uncommon because sometimes there's some part of the code which is fine-tuned for higher performance, and sometimes that is written in assembly. And that is likely to have a higher defect density. So you could assume that assembly has a 40% more defect, then you could make the factor, calculate the factor this way. 1 plus 0.4 multiplied by fraction in assembly language.